In this video, we're going to take a look at momentum and impulse, which is the beginning of our new topic of study. Big difference between what we did in the last unit on energy and this one is we're dealing with vectors all the way through again. So you will need to watch out for that. This is kind of a little history of how the full kind of momentum understanding has developed. We understood something about momentum before, but when looking at nuclear physics, neutron decay, saw kind of weird things happening. And the reason it's bothered them was that we had this idea from Newton that momentum should be conserved. And so it looks, and hopefully you'll see this after we go through our definitions of momentum, that there is something there, that momentum has to be conserved, that if the object was at rest in the beginning, then the whole system must have this net momentum that is zero at the end. In this particular kind of situation, this is what we call an explosion. Not necessarily a violent explosion, which nuclear decay can be, but explosion nonetheless. And we'll look at that more. So momentum. Momentum is defined as mass times velocity. Momentum is a vector. It has the same direction as velocity, and the mass of the object multiplied by velocity gives us, its velocity gives us the momentum. This is actually true of a whole system as well, and we'll look at how we deal with a bunch of individual particles combining together to become one big system as we go. So the unit is a little bit of a trick question if you want to think of it that way. The units are kilograms times meters per second. Also, it can be given in newtons times seconds, but we don't rename that. We just keep it as a kilogram meters per second or a newton second. So momentum, in this case, we're talking about linear momentum, just traveling in some direction v that v is in. And this is the same direction that momentum is. P is the value for momentum because when Newton talked about it, he called it impetus. And so we get the P from there. For our symbol, usually we use a lowercase p when it's an individual object and a capital P for a whole system. But let's be honest, we're not really that careful about it always. So just watch out for that. So where does this all come from? Well, it's really just another way of thinking of Newton's second law. We've been saying net force equals m times a, but we also know that the acceleration is the time derivative of velocity. And so if we sort of spread that out and say, well, mass doesn't change with time. So if we put that inside, we could do the derivative of mv with respect to time. And this is really how he described it. He said, well, there's this rate of change of impulse, of impetus, of this momentum over time that gives us the net force. And so net force is dp dt, the change in momentum. And this is kind of a more general statement, really, than F net equals ma, because we don't really need to know the acceleration rate per se. And this one can actually help us when mass is not a constant. And that's nice because if you think of a rocket being launched into space, right, the mass of the rocket changes as the fuel burns. And so this can allow us to solve that kind of problem as well. So you're just this close to starting to look at rocket science, which is kind of nice. Two possible situations, right? If you have a net external force, the momentum changes. And that's Newton's second law. We're going to kind of look at what that is in this video. But then there's also the case where, well, what if the net external force is zero? Well, then the dp dt would not change, and we would say that the momentum is conserved. And so this will get into our second of the conservation laws that we're talking about. So when we say a change in momentum, you can visualize this by just dropping a ball that bounces off the floor, right? A 1 kilogram ball hits the floor with a speed of 20 meters per second. It rebounds at 10 meters per second. Now, this is much more realistic than kind of the situations we've looked at before, right? Things don't bounce back perfectly to their original height. They lose some energy. And although we're not going to talk about energy in this problem today in this video a lot, you will notice that the amount of kinetic energy we have before and after the collision is actually different, right? If we were to look at this through the lens of Unit 4, we would say there is a loss of mechanical energy, which means we had work done by a non-conservative force. And that would be the normal force of the ground acting on it. And you always know that because you can hear a sound, right? You hear the sound of the bounce. That kind of energy is vibrations in the air, and that's really just thermal energy. So what is the change in momentum? Well, this is actually set up as a clicker question, but of course you're not looking at it right now. You should pause the video and think about it. We have a change in velocity of 30 meters per second, and the mass stays the same. So the change in momentum could be mv final minus mv initial, or just mass times v final minus v initial. And it is an upward force, or an upward, change in momentum. And that's because that is the direction of the change, right? We started out downward and we ended up upward. So we must have had a net force, or the normal force in this case, that is in that direction. So F net equals change in momentum over time. And we can rearrange that and put it into its integral form. And in this form, we would say F net dt equals dp. And then if we integrate or sum both sides, we actually get the change in momentum. And so this quantity, the integral of the net force dt, is called the impulse. So the force over a time is the impulse, and this is equal to a change in momentum. And this is our statement: an impulse causes a change in momentum. In the same way that we used to say a net force causes an acceleration, right? These are parallel ways of thinking about changes in motion. So the impulse. What are all of our units? Well, it's Newton seconds is usually how we define impulse, because it's defined as force times time. But that, of course, is the exact same thing as kilograms times meters per second, because it's a Newton, a kilogram, meter per second squared times a second. And the direction of net force, impulse, and change in momentum are all the same, which hopefully adds, understanding to it. So here's an analogy. We have the work kinetic energy theorem that says that the change in kinetic energy has to do with the work done by the net force, right? And then now we have what we call the impulse momentum theorem that says the impulse from a net force causes a change in momentum. Both of these refer to a change in how fast an object is moving. The net work one only cares about how fast it's going, because that's change in kinetic energy. The impulse one actually tells us about the change in direction. So they have overlapping ideas, but they tell us different things. So if we were to think about the impulse, say a force applied over time, if it's a constant force, then the force versus time graph is a rectangle, and the change in momentum is just a very simple area, force delta t. And so that works if we have a constant force. What if we have something that's not constant? So here's a little video for you. This is a high-speed shot of a tennis ball hitting a wall. Right, and you can see the deformation of the ball as it goes through that contact, hitting the wall, being changed in direction. Right, so here's kind of a little picture of what's going on. This is actually a snapshot of a racquetball, not a tennis ball, but it shows up better because it's blue on the background. The thing you will notice is that the force of the ball on the wall and the wall on the ball are equal in magnitude and opposite direction. That's Newton's third law. That didn't change. Right? But the amount of force changes over time. When it first hits, there's just a little bit of force. At some point, you get to your maximum compression or deformation, and you get your biggest possible force, and then it kind of pushes up off the wall. And so if you were to graph this, you would look at something that looks like this. As it hits, you would have some sort of curve. It would not necessarily be perfectly shaped. It all depends on how that force depends on the deformation, which is not Hooke's law, although it could be approximated if you needed to. In that, you could just make this into a triangle for a rough approximation. But the area under this curve would be the impulse. Now, if this followed a particular force versus time curve that you could actually integrate, like maybe it was net force depends on time squared or something like that, maybe it's a parabolic shape, what have you, then you could actually compute this integral. If not, we would estimate the area under the curve. So this is an example, something you can try, right? These two have essentially the same area, but we're doing something different. So if you were to jump up in the air and land without bending your knees, right, you don't have to jump super high, you would feel a big force for a short time, and it would stop you. And that's what it does. It takes you from moving downward to rest, as you would. If you jump and land with sort of bended knees, then you can lengthen the amount of time that it takes for the collision to occur, for the stopping, but lower the maximum force. Right? Same delta P, because you have the same velocity as you come down and hit, but then you spread it out over a bigger time. This is the principle behind an airbag and a crumple zone in a car. The idea is that you slow or you lengthen the amount of time, which is to say slow how fast you stop, and that allows you to reduce the maximum force. So here's a simple example. A 10-kilogram pig initially at rest. Net force on the pig lasts for 4 seconds. What's the final velocity of the pig? So we use impulse equals change in momentum. The initial momentum is 0 here, and so we have our integral. This is a pretty easy area under the curve, so we don't even need the integral form, just 1/2 base times height, and we end up with 12 meters per second. This works in 2 dimensions as well. We just need to break it apart, right? So we have 20 meters per second. This is a perfect collision, right? You still have all of your speed after it. But what we need to do is think about, well, there's the final momentum. There's the initial momentum, or the negative of it. If we subtract the initial from the final, we find that the impulse was straight up, right? And hopefully that makes sense, right? The component of velocity horizontally in the x direction didn't change, but in the y direction it did. So the change in momentum then is going to be equal to the 10 Newton seconds that we had at the beginning, 10 Newton seconds at the end for our momentum. Since we're finding the hypotenuse of a right triangle, we find that it's 14 Newton seconds upward. So how much force was exerted in this case? You can go one step further and try to find that, but we don't have any idea in this case, right? We don't have any information about that. We could talk about how impulse is change in momentum and try to figure out that force, but what would we need? We would need information about time of collision, and we don't have that information, so we can't solve for it. All right, here's that airbag example I alluded to, right? You have a car moving at a particular speed, collides with a tree, and they stop. The airbag brings the 60-kilogram driver to rest in about 0.7 seconds. What's the average force exerted on the driver? Notice I'm saying average because I don't know force as a function of time. I can't tell you the maximum force or the force at any given time, but I can say, well, my change in momentum over time should give me the average force. So we could plug that information in, and you end up with about 1,000 newtons. Negative in this case because it's in the opposite direction of the change in velocity. And again, we're back to negative signs representing direction because we're talking about vectors here. The airbag increases the time and decreases the force. That's its purpose. It's also the purpose of the crumple zone, which you kind of see at the front of that car. All right, one other example. If F is a continuous force, like say water spraying out of a hose, right? Fire hose, 30 kilograms of water per minute hits a brick wall with a speed of 85 meters per second. What is the force on the wall? Again, we're talking about sort of an average force here. Change in momentum over time gives us our average force. This is the change in momentum. We know that the final momentum is 0. It stops after it hits the wall. And so what we really need to do is think about how much time. Well, if we have 300 kilograms per minute, we may as well pick, I don't know, 60 seconds and say that's 300 kilograms times 85 meters per second for the mass and velocity divided by 60 seconds over which this happens, because that's the same as saying we have 300 kilograms per minute multiplied by 85 meters per second. So it gives us the same thing. We get about 425 newtons. So that's the force that the water experiences to stop. And if it wants to know the force on the wall, that would be the opposite, positive 425 newtons. Newton's third law again. So that's it. The big idea here is that impulse is some force applied during some time interval, and it causes a change in momentum. This is really the impulse momentum theorem, just a restatement of Newton's second law, or maybe going back to the original statement of it. And remember, momentum is mass times velocity, this vector quantity.